Yeah, if you're taking like calc, I don't any of the calcs really, I think you have a lot of midterms. Yeah, I'm still in school. I'm a grad student, so yeah, that's why that's one of the reasons why I'm teaching this class. Yeah, I
Oh,
take.
perfect.
Mm-hmm.
Yeah, what do you call it? The quiz three was a lot easier than the other two. It was a lot easier than the other two quizzes.
Mm-hmm. Yeah, we're gonna talk about quiz 3. So yeah, I'm not getting my PhD. I'm a grad student here at Cal State Fullerton, and they, at least for mechanical engineering, they only offer masters. So I'm working on that. So I'm gonna pull up quiz 3, make sure what the average was. So there was a lot of you on quiz 3 that got 100%, which is good. It's a lot better than getting like an F or something. So quiz 3 is kind of like a rebound quiz, I guess. Okay, so the average for quiz 3 was at 73%, so it's still not like, this a really high average or anything, but it was better than quiz 2 for sure, and I think quiz 1 was around a 73% average too. So again, a lot of you got a 100 on it, and this quiz is probably easier really than a lot of the quizzes we're going to have, because really what you could have done is just gone into MATLAB, typed out all of this stuff yourself. Like, you could have made all the vectors and the matrices yourself, and did the whatever operation we had, and you could have seen the size right away, or if we could or couldn't have done it. So really, I don't really like that, because it's not really showing me that you understand why something does or doesn't work. So if we were doing this class in person, I basically would have disabled MATLAB on the computers, and you would have had to actually like write down, on with your pencil or on the computer, however I would do. Who cares? But I would have disabled MATLAB, and I would have had you actually think about, can we do this operation, and what is the size going to be if we can do it? And that way, I'm actually testing your understanding, and not just, can you type it into MATLAB and see if it works or not. So yeah, testing this kind of stuff virtually is really hard, because I can't, really say that you can't use MATLAB. I can't really enforce that. So for this quiz, it was kind of difficult to test you well. So yeah, there's a lot of 100%, and if you didn't do well in this quiz, that's still okay. It's only one quiz, right? But I want to make sure that everyone understands how to do this stuff. So we're gonna have a little review again. There was a request to do it, and I think it's a good idea to make sure that, because again, not to be a broken record, but you could have just typed all this stuff in MATLAB and basically done really well in the quiz. But I still don't really know that you have a good understanding yet on this stuff. So we're gonna do a little review for the last time at the very beginning of class. Homework 3 is not graded yet. I'll probably grade that today, or I don't know, sometime by the weekend. But that's just, of course, on completion. So if you completed it, actually gave it an effort, and you did all of it, then you're gonna get 100%. Oh yeah, and I think I put it as, like, it might say right now that it doesn't count towards the final grade. It does. I just did that so it doesn't count against your grade yet, because there was an issue last semester where if I didn't grade stuff right away, Canvas would show like a 0 because I didn't grade it yet, and it would affect your grade. But don't worry, the homework is going to count towards your final grade. You just gotta wait till I grade it. Okay, let me go to today's page. So we're going to be doing that review again. So I spent a good amount of time on this last night to make this review. So if you want to pull up the slides, I have the updated slides on Canvas. So we'll do this review, and then we're going to do a little exercise for plotting again, and then we're going to continue the plotting chapter. So there's not going to be any homework today that I assigned, just because we're not going to get through enough stuff today, but I'll probably assign it on Monday. All right.
I'm sorry, can I repeat that?
Yeah, sorry, it's raining hard now. Nice. So there's no homework that I'm going to assign today just because we're not going to get through enough stuff. But I'll assign it on probably next Monday, on this upcoming Monday. Any updates on the project? The project I'll probably talk about later this month. I think that's what's shown on the syllabus. But it depends on how much we get through, because we need to get through all of plotting, and we also have to go through some of the chapter for functions. I think that's chapter 3. So nothing yet, but it's going to be similar in structure to last semester's project, which was on COVID-19 data. So basically, I'll give you some data, and you will have to reduce this data down to something where you can plot it. So it's basically data visualization. It just kind of stopped. Yeah,
You did
that's weird.
say you did say that if we do well, you did say if we do well on the projects 1 and 2, we should able to pass this class. Is that right?
Yeah, you should, because the projects are 60%. So let's say you got 100 on both of them. That's a little, that's ideal, right? So I think there's 60% in total. And assuming you did all the homework, that's, I think, 15% or something. And then the quizzes, that should help you a bit as well. So if you do well on the projects, I'll keep that in mind too. Because if you show me that you did well in the projects, then that tells me that you've learned a lot throughout the class and you can actually apply what you learned. So that'll be taken into account as well to like boost your grade a bit. If you're close to like a B or something. So I have a kind of qualitative grading as well if you're close. All right, so any other questions before we get started on the last review? Yeah, for the first project, I forget if anyone did for that one. And the second one, and they're related by the way, the projects are related. Basically, the second project is doing a lot of the same, or getting a lot of the same results for the first project, but we use programming techniques. But I think a few people got 100, maybe like 1 or 2, but that's not to say I graded them hard. A lot of people did get A's, but only a few were perfect for everything and got 100. Okay, so I'm gonna open up a new script here. Oh yeah, and next week I'm kind of playing with the idea. I think it would be good to have a little plotting kind of workshop with the class. So basically I'll give you some data on Canvas and we'll go through this. We'll import the data as class, and then we'll basically do some manipulation for this data and then plot it. And that'll be like a little kind of intro for what we're going to do in the project. It'll be very simple for our workshop, but it's also going to provide some good context for all of the stuff we've learned so far. So I think that'll be helpful. Is it tough to get a good grade on the projects? No, I don't think it's tough. Because you have a lot of time to work on the project, like you're going to have at least 2 weeks. And again, it depends on when we actually get to the project, but you're going to have at least 2 weeks to work on it, probably 3 or maybe even 4. So it's not like a quiz where you're not going to be able to, or where you have to just get things right away, right? So if you don't understand something, you have time to work on it. And if you can figure out whatever the issue is, and you get the correct result, and then you type up your report, you're going to get a good grade. So I wouldn't say it's difficult, but it's going to be a good amount of work. Not an insane amount of work, but it's going to be a good amount of work. EGME 205 03 10. Okay, so again, we're going to be doing some, basically this last review on matrix multiplication and array operations, because I really want to make sure that all of you understand when we have to use each method and if it's going to work or not. Because throughout the rest of the class, more so we're going to be using element by element multiplication really often, just because we have vectors really often, and a lot of times we're doing operations on those vectors. So you'll need to know when we have to do an element by element operation or not. Okay, last review. Okay, so the first thing we'll kind of go over here is matrix multiplication. So I think this is actually maybe easier for a lot of people to understand, just because there's some really straightforward rules that we have. So the first thing that we want to do is look at the matrices that we have and make sure that we put them down in the correct order. So what I mean by that is, are we doing A times B or are we doing B times A? Because that's, the order does matter. And then once we do that, we're going to write them down. So we'll write down the size of A and the size of B if we're doing A times B. And then we compare the inner numbers. So when I say the inner numbers, I mean this number here and this number here. So if n was 2 and m was 2 here, they're the same. And if they're the same, that means we can do matrix multiplication. If they're different, then we can't do it. So assuming that we can do matrix multiplication, then we're going to look at the outer numbers that we have, and they're going to tell us the size. So it'll be m by n for the size, looking at these outer numbers again. So we have an example here. Let me do this. Okay, so I'm going to go through this one somewhat fast just because, again, I think that matrix multiplication is actually easier to understand. Even if you didn't take 250B yet, I think it's a little more easy. I need to put semicolons there. Okay, so we have a column vector A, and then we have a row vector B. Now, of course, these are vectors. They're not matrices, but we can still do matrix multiplication. And you can actually even really say that a vector is a type of matrix, technically. But either way, we have these two vectors, and we can still do matrix multiplication between these two vectors. So the first thing that we do, we want to make sure that we can actually do this multiplication. So if I'm doing A times B, I would personally recommend that, yes, you can look at this and you can think about it in your head what the sizes are, but you can be really explicit with yourself and just write them out yourself to see if you can do the multiplication. So we're doing A times B. So this is going to be, we have 3 rows and 1 column for A. And then for B, we have 1 row and 3 columns. So we look at the inner numbers, they're both 1, so that means that we can do the matrix multiplication. And then we look at the outer numbers to see what the size is going to be. And in this case, it's 3 by 3. So we're going to get a 3 by 3 matrix. And I also showed you guys in this example the actual kind of math that we're doing here. So it would be 1 times 3, 1 times 5, 1 times 6. And so this is, I wasn't intentionally doing this, but kind of by happenstance. This particular example, if we did element by element multiplication for A times B, it would actually be the same exact result. So we'd be doing, again, 1 times 3, 1 times 5, and 1 times 6. But we're going to talk about some of the more particular rules of element by element operations in a second here. So a lot of the times, the result that we get for matrix multiplication and element by element multiplication aren't going to be the same. But for this particular example, it just so happens to be that it is going to be the same. Alright, so we're going to do A times B, and we're doing, again, element by element multiplication. So we put in our little period before the operation. I should make this a capital C, because we're getting a matrix. And there we go. Here's our result here. Oh, sorry, we're doing matrix multiplication. But, you know, we get the same exact result. Let's do this. D equals A times B. And then if I type both of these in the command window, you're going to see that they are the same exact result. Okay, so now let's go over array multiplication, which is just another term for element by element multiplication. I forgot to add little pauses on the slide. I want to go through this kind of section by section here. So I know this is quite a busy looking slide. So the first thing that we're going to look at is two vectors of the same type. So when I say that, I mean like two row vectors or two column vectors. So if we're doing element by element multiplication for two vectors of the same type, the lengths have to be the same because we need an element for every element that we're doing an operation on. So if we're looking at A times B, we have two row vectors and they're both a size of 1 by 3. So both of these vectors have 3 elements in them. So if I do A times B element by element, basically we're making a whole new vector, we'll say C in this case, where we do 1 times 3, that's position 1, and we do 2 times 4, that's position 2, and then we do 2 times 5, that's position 3. So that's going to work out for us, so I put a little check mark here. But if I do A times C element by element, we have two row vectors here. And because we have two row vectors, they have to be the same length. And in this case, they're not. So A has a magnitude of 3, or a length of 3, and C has a length of 4. So we're doing 1 times 6, that's good. 2 times 7, that's good. 2 times 8, that's good. But at this point, we don't have a fourth element in A. So MATLAB kind of freaks out because it's looking for that fourth element in A, so we can multiply that by the fourth element in C. But again, there is no fourth element in A, so it's not going to be able to do this operation. So we put a little X there. All right, so let's go through this. So let's define A. So we have 1, 2, 2. We have B is 3, 4, 5. And can't type today. C is 6, 7, 8, 9. Sure. The first exercise that we did was matrix multiplication up here. But we also did element by element on this one line, just to show you that for this specific example, both of the results were actually the same. Okay, so first thing we're going to do is A times B element by element. So, what should I call this? P1. Okay, so we have two row vectors and they both have a length of 3. So because of that, we know that we can actually do this operation. So I'll do A times B element by element. And if I run this, then we get P1 in the command window. So good. If I do P2 equals A times C element by element, A has a length of 3 and C has a length of 4. And they're both row vectors. So because of that, they need to have the same length. But they don't. So that's going to indicate to us that we can't do this operation. So if I run this now, then we get an error, and it shows line 22, which is this line here, and it says that the matrix dimensions must agree. All right, so that's why we can't do that. We'll do P3 equals A transpose times B transpose. So, when we do this, really all we're doing is taking our row vectors, we're transposing them. So in this case, we're trying to do element by element multiplication between two column vectors. So we have two column vectors, so again, those lengths have to be the same. So we have basically a 3 by 1 multiplied by a 3 by 1. So we're going to be able to do this. I'm going to comment out this line because if I run this right now, we're going to continue to get this error because MATLAB goes line by line for our script. And if it can't get past this line 22, it's just going to stop. So I'm going to comment that out. Alright, so here's P3. So we get a result of 3 by 1. And then we'll do P4. We have A transpose. So that's a size of 3 by 1. Multiplied element by element with C transpose. So C transpose is a size of 4 by 1. So we have these two column vectors now, and they have different lengths. So because of that, we're not going to be able to do this operation either. And we get our error that says the matrix dimensions must agree. So I'll actually put a little comment for the ones that don't work. And so we had a 1 by 3, and then we had a 1 by 4. And they were both row vectors. So it didn't work. And then here, I really should put a percent sign there too. Then for this last one, we had a 3 by 1 and 4 by 1, both column vectors, so that didn't work. I'll say nope, because it didn't work. Alright. So now let's go into the next section here. If we have a vector and a matrix. So, a lot of the times for these element by element operations, you can just kind of look at them and you can kind of just think through, is this going to work or not? But, I was trying to break all of this down into different sections here and really think about the kind of language so I can make these little definitions here. So I think I got all of the different possibilities, but if I didn't, I guess let me know. But in this case, if we have a vector and a matrix, the magnitude of at least one dimension of the vector must be the same magnitude as the dimension of the matrix. So that's kind of a lengthy, kind of thing here. But an example is if we have a vector here, which has dimensions of m by n, and we have a matrix over here, which has dimensions of m by n, if the size of m for both of these is the same, then we're going to be good. So we'll go through an example to kind of make a little more sense of this. So we have this vector A, again, it's a row vector, and then we have two matrices B and C. So the first one that we're going to do is A times B. So for this, A has a size of 1 by 3, and B has a size of 2 by 3. So you can see that both of them contain the same magnitude or length for the columns that they have. A has 3 columns and B has 3 columns. The rows that they have are different, so A only has 1 row and B has 2 rows, but because both A and B have 3 columns, then we're going to be able to do this element by element multiplication. And then our size in the end is going to be a size of 2 by 3, which is the size of B. So you can kind of think of it this way, where this entire row vector is going to be multiplied element by element with each row in B. And then if we do A times C, we have 1 row in A, we have 2 rows in C, so that's not, nothing is satisfied yet. So if we're going to do this element by element multiplication, at this point we're banking on both A and C having the same amount of columns. But A has 3 columns and C has 4 columns. So in this case, neither the amount of rows between these two are the same, and the amount of columns between the two of these aren't the same. So because of that, this isn't going to work for us. Okay, there's a question. So for vector matrix, we don't look at the inner numbers. No, I want to kind of emphasize that for looking at the inner numbers to see if something is going to work, You do that for matrix multiplication, not for element by element multiplication. At least explicitly like that. I know I said, in this case, M and M, for my little example here, they were the same. That's kind of like this example down here, where, both N and N are the same for B. And when I say that, I just mean that both A and B have 3 columns. But when you look at the inner numbers to see if multiplication is going to work, you always do that for matrix multiplication. Yeah, this is element by element. Up top here it says array multiplication. That's just another word for element by element multiplication. Okay, and you can see it too with the period before the multiplication as well. Okay, so let's go through this now, and hopefully it'll make a bit more sense too. So we have A up here, that's already defined. And now let's define B, capital B, is 2, 2, 2, and then 3, 3, 3. And C is going to be 6, 6, 6, 6, 7, 7, 7, 7. So I'll do P5. So we're doing A times B, element by element. So let's do A times B. And if I run this now, it's going to work out for us. So I'll pull these up again. So again, what we're doing, we have a vector and we have a matrix, and we're trying to do element by element multiplication. So if I have a vector and a matrix, then the amount of rows between these two arrays that we have needs to be the same, or the amount of columns between these two arrays has to be the same. So if we first look at A and B, we see that A only has 1 row and B has 2 rows. So far, our requirement to successfully do this operation isn't met. So at this point, we're going to hope that we have the same amount of columns between the two. And so A has 3 columns and B has 3 columns, so that's good. So now we can do this element by element multiplication. And then again, we're kind of doing 1 times 2, 2 times 2, 2 times 2, and 1 times 3, 2 times 3, 2 times 3, which you can see down here. Right, and then the other one that we're doing, we have P6 equals A times C. So the amount of rows between the two are different. A has 1 row, C has 2 rows. So that's not meeting our requirement yet. So then we hope that we have the same amount of columns. A has 3 columns, C has 4 columns. That's still different, so we're not going to be able to do this. So if we run this now, we get to this error on line 29. It says we can't do it. And again, it's because neither the amount of rows or the amount of columns are the same. So we had a 1 by 3. Then we had a 2 by 4. So we have a row vector and a matrix. And then I'll say nope once again. Not bope. Nope.
So one of the lengths has to be the same, except if it's 1 or what?
Yeah, if you have a vector and a matrix, one of the dimensions needs to have the same length.
Excluding 1, right?
Excluding 1?
Because 1 times 3 and 1 times 4, you can't element by element that. Right?
What do you mean for this example?
No, the element by for like P1 and P3. Or sorry, P2 and P4.
Yeah, I mean that's a different kind of problem we were looking at for P2 and P4. That was up here. That was for 2 vectors of the same type, so 2 row vectors or 2 column vectors. And that's when we didn't have, for that, the lengths have to be the same if they're the same type. Yeah. Okay, so the next one is when we have 2 matrices and we want to do element by element operations between them. So, here I said the magnitude of at least one dimension has to be the same. If the magnitude of both dimensions were the same, then that's kind of when we get to here. So if we have 2 matrices, then these sizes have to be identical. So if we have like B and C here, B has a size of 2 by 3 and C has a size of 2 by 4. So they're different, so we're not going to be able to do this. And again, it's somewhat similar to having two vectors of the same type, where we are running out of indices. You know, the amount of elements that we have in both of these matrices have to match, because we're going to be doing 2 times 6, 2 times 6, 2 times 6, and C has 4 elements in this first row, but B only has 3. So MATLAB is going to look for this fourth element in B, but it doesn't exist, so it's not going to be able to do this operation. So we'll just show this. P7 is B times C. Now if I try to run this, let me comment out P6. Then we're going to get an error once again where it says our matrix dimensions have to agree. So we have a 2 by 3 and a 2 by 4. Jeez. Nope. Alright, so we have one more thing to go over, which is if we have two vectors once again, and they're of different types. So, you know, in the previous slide, we had two vectors of the same type, so that means like 2 row vectors or 2 column vectors. But we can also do this where we have 2 vectors of different types. So if we have a row and a column vector, or a column vector and a row vector. And little hint here, this is what we did basically with this matrix multiplication example, right? We had a column vector here and we had a row vector here. And we saw that both matrix multiplication and our element by element multiplication for this specific example, I should say, the result was the same. That's not going to always be the case. So sometimes you might be able to do like element by element multiplication, but not matrix multiplication. Alright, so let's take a look at this. We have a row vector A, which we already defined up here. And then we have 2 new column vectors that we'll define. So we have 2, 3, and 4. That's R. And then S is going to be 2, 3, 4, and 5. Okay, so for 2 vectors of different types, and again we're trying to do an element by element multiplication in this case, the lengths do not have to be the same. So if we have 2 vectors of the same type, the lengths have to be the same. But if we have 2 vectors of different types, the lengths do not have to be the same. So if I have a row vector and a column vector, it doesn't matter if the lengths are the same or different. We can do this element by element multiplication. So if I do A times R, let's make this bigger. If I do A times R, we're basically going, well, element by element here. We're taking this first, or we're taking this row in A, and basically multiplying it by every row in R. So we're doing 1 times 2, 2 times 2, 2 times 2, that's the first row. And then we do 1 times 3, 2 times 3, 2 times 3, second row. And then the third row is 1 times 4, 2 times 4, 2 times 4. So our output in this case will be 3 by 3. And you can kind of see that where we have 3 columns in A and we have 3 rows in R. So that'll be a 3 by 3 matrix in the end. Right, and then, so again, the lengths don't have to be the same. So maybe I should say the magnitude of the length doesn't have to be the same. The magnitude of this length for A is 3, and the magnitude for this length is 3 as well. And we could have A, which has a length of 3, and we could have S, which has a length of 4, and we could still do this element by element multiplication. So basically, we would just add on a whole new row here, which would be 1 times 5, 2 times 5, and 2 times 5. And so for this, we would have an output size of 4 by 3. So we have 4 rows in S and 3 columns in A. So I'll show you this, and then we'll be done with this review. Took a little longer than I wanted, but that's okay. I want you to understand this stuff. So we have P8 is A times R, doing this element by element. And then we get a 3 by 3 result here. And then P9 is A times S. And basically you're going to see that we just add on a whole new row here. So this is A times R, and this is A times S. Okay, so any questions on the review?
So, uh, so for the array multiplication, do they have to be the same?
It depends on what you're trying to do. So that's when you would look at all of these different kind of scenarios that I listed out here. Because it depends on the size that you're trying to do this element by element multiplication on. So I would look at each kind of section that I laid out here. And then it depends if the size has to be the same or not. So I tried to lay out every possibility that you could have. So if you're trying to do some array multiplication, you could reference this slide again, and you could see which kind of scenario that you're in, and then you can determine if you can do it or not. Okay. Anything else? Okay. Someone's mic is on too if you don't know.
Oh, that was mine. Sorry.
Okay, that's okay. Alright, so let's finally go to plotting again. So I know this took a while, but I want to make sure again that everyone understands this stuff. So I was going to have you do a little exercise, but you know, this took a lot of time, so we're not going to do that. But I do want to go over plotting polynomials again, because this will be something that's relatively important for I don't know, plotting in your general use in MATLAB. So plotting polynomials. So let's say that we have an x range going from 0 to 20. So I'll do x equals 0. We have a step size of 0.01, and we're going to 20. And let's define some polynomial. In this case, that's 50x cubed plus 20x squared plus 5x plus 9. Let's say a polynomial, just so we're very clear on what we have. So this is 50, 20, 5, 9. So remember, to make a polynomial, it's really, we make a row vector, but depending on our usage of this row vector, MATLAB can interpret it as a polynomial. So this is currently representing 50x cubed plus 20x squared plus 5x plus 9. So if I want to plot this polynomial along this x range that we have, we need to make sure that the length for our x range is the same as the length for our polynomial. So if I was currently just going to do plot x comma polynomial, that wouldn't work, because we have this length of x, which is 2001 elements. You can see it in our workspace over here. And then we have basically just some row vector that happens to be called polynomial that has a length of 4. So when we plot stuff, the lengths have to be the same. And also currently, you know, MATLAB isn't interpreting this as a polynomial yet. It just sees it as some row vector. So what we're going to do is we want to evaluate this polynomial that we have here to get its corresponding y value for this range that we have, for this x range. So to do that, we're going to use the function called polyval. I'll do polynomial eval. I know, really long variable here. Okay, so we're going to do polyval. And the arguments for this is to first give the polynomial that we want to evaluate. So for us, that's called polynomial. And then the second argument is the x range that we want to specify. So for us, that's just x. And again, this is going to evaluate our polynomial here to get its corresponding y value for all of these values for the x domain that we have. So let's run this, and then if I open up polynomial eval, you see that it's a length of 1 by 2001, or we have a length of 2001 elements in here. Okay, so if we open this up, you see that our polynomial, it's now evaluated again for all of the x range. So we have all of these kind of y values for that x range now. So we have two vectors, x and polynomial eval, and so we can now plot this polynomial. So we'll do plot. First argument is the x domain that we have, so x. Second one is all of the y values that we want to plot, and that's, get out of here, polynomial eval. And now if we run this, let me do, it should actually show up on my computer. I think there's this kind of weird little glitch where if I run it, my plot isn't showing up. So I need to do figure, visible, and on. And then it'll show up. There we go. And here is our polynomial that's, that we just plotted because we evaluated it for all of the values in our x domain. Okay, so that's how we do that. Okay, so now we're gonna basically go back to where we question.
Patrick, yeah, what does visible on mean again?
Yeah, so visible and on, that just is for our plot to show up. So it's basically a command to say if we want our plot to show up like this or not. So if I change this to off and I run the script, then the plot doesn't show up anymore. So that'll be useful when we have like a ton of plots in one figure.
Oh wait, so okay, see, so it's telling the figure when you say figure, you're talking about the graph, is that right?
Yeah.
I see. And you need to put visible but when you say on, that means you're showing it, but if it's off, then you're not showing it.
Yeah, that's correct. Oh, without the command, yours doesn't show up either? That's interesting, because it should show up. Maybe they changed this in the new version, I don't know. Because before, if you didn't have, line 44, all you had was plot, and then whatever, it would show up, but maybe that's a new kind of thing where they want you to either specify figure 1 or whatever the title is, or this kind of argument. Yeah, well, all we have here in my current script is just array operations, so that shouldn't affect the plotting. But yeah, it might be something new, I'm not sure. It's good practice anyways to kind of label all of our figures like figure 1 or do this. Alright, anyways. Good to know though that you guys have the same issue. Okay, so we're gonna start talking about subplots now. So a subplot is basically, it's gonna be a figure that we have, but it is a figure that contains basically an array of plots. And we call those subplots. So basically we could have like, I don't know, you could kind of think of it, I don't know, I can't really think of the word now, but you can imagine we have like a figure up here, we have a figure over here, and then down here, and then over here. So that would be basically like a 2x2 matrix almost of figures. So you'll see what this looks like. If we go to the next slide here, this is an example of a subplot. So we have one figure here, and we have one figure here. But all of this is basically one graph that we made. So this is useful basically if we're looking at like a specific portion of a graph. Sometimes we want to do that. That'd be the most, probably most often case when we use this. Okay. So again, it's just basically an array of figures. So the syntax for this is subplot, and then we have m, comma, n, comma, p. So m, that's going to stand for the row that we want. So if I want to put some figure on maybe the first row, I would do subplot 1, and then if I want it in the second column, I would do 2, and then to specify the pane, I would put whatever. Oh, I even have an example here. So subplot 3, 2, 5, this would put a figure in the third row in the second column, and it would basically correspond to the fifth pane, which would be in the bottom left-hand corner. What does B do? Where do I have B here? Am I on this slide? Or do you mean P? Oh, previous slide. Which one? I've gone through it kind of a lot now. This one? Okay. Oh, it might be for the color that you're looking at. On line 12 here. Yeah, so that's going to stand for the color. So we'll talk about specifying color in more depth later on too. But that just makes this plot blue. And up here you see I have M, which stands for magenta. And it gives us that kind of pinkish color. So pane, that stands for basically the position that we have. So this figure here would be the first pane, and this position here would be the second pane. So we're going to do this example right now, and we'll kind of get a better idea of what we mean by that. So we're going to make this plot here, which again, it's a subplot, so it contains two figures, or two plots in this figure, however you want to say it. So you see, basically this is one whole coding block here for this first figure. And down here, it's a whole coding block for the second figure. And you see that we first define x and y, and then I say subplot 1, 2, 1. So I'm telling MATLAB that for my subplot that I'm creating, I want to have one row of figures, and I want to have two columns of figures. And for this current plot that I'm going to plot right now, I want this one to be the first pane. So that's this one here. And then for the second block of code, we say that, we still have a subplot of one row and two columns. So I say subplot 1, 2. But I want this block of code to be the second pane. So that's why we put a 2 at the end here. And that corresponds to this one right here. Okay, so let's go through the actual code now. So let's first define, I know my text is really small, so it might be hard for you to read. But for the first figure, we're going to do x. This is our x domain. So from 0 to 5, and we're going to have a step size of 0.01. And then our y kind of function that we're defining here is going to be e to the negative 1.2 times x. And then, so look at this, right? This is a vector right now. Let's first run this. And if I do size of y, this is a row vector with 501 elements in it. And we're taking this vector, e to the negative 1.2 times x, and I want to multiply this by sine of 10x plus 15. And that's also a vector. Let's, for now, I'm going to go down here, and I'll say sine of 10 times x plus 15. So we have size of y and size of y1. So these are both row vectors. And we're doing multiplication between these row vectors. So what do we want to do? You can see it. We want to do element by element multiplication. So we need to remember that we need to put in that period. Let's go back here. So times sine of 10 times x plus 15. So make sure you put that period in there because, again, we want to do element by element multiplication between these two vectors that we have. Alright, so we have x and y, and now we're going to do our subplot here. Let me add more comments just to be very clear what we're doing. So define x and y vectors. Make subplot. So we're going to use our command now, subplot. And we want to have one row of figures and two columns for this. And this current figure that we're about to plot, I want to have this in the first position or the first pane. So we're going to put 1. So this is basically just kind of setting up, what we're going to do. Let me also do figure, visible, and on. Visible. Okay, and now if I run this, you see that it has room for another figure over here, but it didn't show up yet because I only specified one subplot, which was 1, 2, 1. So MATLAB basically has room where we have one row here, and it has room for another column or another pane to be inserted here. Now, of course, I didn't plot anything yet, so it's just empty right now. So let's actually plot something now. So this is going to show up in the first pane. Let me put that there. So we're going to do plot x comma y. Well, now let's run this. Oops. So now if we run this, now we have a figure that's in our first pane. Because again, we did subplot 1, 2, 1. That corresponds to this pane. And then we plotted x comma y, which is this nice looking function here. Okay, so now we're going to add on some more things here. So we're going to make this pink or magenta. So to do that, I think we briefly talked about it before, but we'll talk about colors and line markers in more depth later on in these slides. But if I want to make this pink, I'll do comma, and then in single quotes I'll put M, which stands for magenta. And then I'll make this line width 1.5. So let's run this again, and then we get this. So it looks good, but one of the things here that we see is that, this curve, it stops around 5. So I don't need to see it go all the way to 6. So we're going to adjust the axis. So we learned how to do this in I think last class, how to use the axis command. So we'll type in axis here. And then in our parentheses, we need square brackets. And then the first kind of 2 arguments that we have is our x range. So we want to go, in this case, from 0 to 5. And then for our y range, we want to go, we'll keep this basically the same, which is negative 0.8 to positive 0.8. And if we run this now, then our graph is a little better constrained. Yes, for this example, there's only 2 panes, but you could make this, even more. So if I wanted 3 panes, then I would have done subplot 1, 3, and that would allow us to have 3 columns, and then 3 panes within that one row. Okay, so we could do this axis command, or because we only changed the x range here, I can use a command called xlim, which I believe we talked about last class, but it'll also be in a future slide. So since we only changed the x limits, I can just use xlim and then 0.5. Run that, and then we get the same kind of thing here, where all we did was adjust the x range. And so we could put in a legend here, but just for, sake of time, I'm not going to put in the legend for this example, but you can refer to this slide if you want to see how to put in the legend. It's just like we have learned so far throughout the class. We just type legend, and within that we put our equation that we want to have. And don't forget that if you have an exponent term, that you need to put that entire exponent term, if it's multiple kind of characters, in curly brackets or curly braces, like you can see here for negative 1.2 times x. Okay, so let's make our second pane now. Let me do pane 1 there. That'll be a little more clear. Okay, so now we're going to make subplot pane 2, because we want to have one over here. Question, so what does the axis do again? The axis command here on line 57, that allows us to change the limits for both the x-axis and the y-axis. So this argument here, 0, and then you need to have a space in 5. That means that I want to have our x range go from 0 to 5. And then here, negative 0.8 to 0.8. That's for the y-axis. So going from negative 0.8 to 0.8. Yeah. And then if we just want to change one of those ranges, like I just want to change the x range, I can instead use this command xlim. Okay, so let's make our second subplot. So for this, we have a different function here. And our x range for this is going to be from negative 5 to 5. So we're going to go from negative 5, use a step size of 0.01, and we'll go to 5. And then our function y is going to be 5 times x to the third. So we're raising x to the third, or we're raising this vector x to the third power. So we need to do an element by element operation. So make sure you put in your period once again. And then we're going to multiply this vector by another vector. And that'll be, in this case, cosine of 5 times x squared. So we do an element by element multiplication here of cosine times 5 times x, 5 times x, and we have x squared, so we have to again use an element by element operation. Okay, let's close out of that. Okay, also I want to point something out, that I have x and y. You know, this is x here, this is y here, and then I have x here and y here. And you know, I didn't call them different variable names. But even though I didn't call them different variable names, which you could definitely argue that I maybe should, I want to point out that it's okay for our plot. It's still going to plot both of these graphs once we get to that, because MATLAB goes line by line. So it's going to go line by line here, and it's going to make all of this first plot, and then it's going to continue down, and it's going to make this second plot. So x and y, they're going to basically overwrite x and y down here. But for this example, just for getting both of these plots to show up, that's okay. Because again, MATLAB goes line by line. So at this point here, the first plot was already made in MATLAB. Okay, so let's do subplot 1, 2, because we have one row of figures that we want to have, and we have 2 columns of figures that we want to have. And we want to put this specific figure on the second pane. So we're going to put comma 2. So if I run this now, it's going to be an empty pane. So there we go. MATLAB knows that I want to have something to show up here. But I didn't tell it what I actually wanted to plot quite yet. So it's empty. So now we can do plot x comma y. And I'm going to do comma b. So again, that's going to make this plot blue, a nice dark blue. I think by default it is blue, but it's a lighter blue than when we specify to use blue. And we'll make this line width 1.5. Alright, we'll run this now. And there we go. Now we have our subplot. I'll make this bigger. So here we go. We have our subplot where we have our first figure, or let's actually take a little step back. So we have a subplot that has one row of figures and has 2 columns. And our first plot that we made, we told the MATLAB to put this on pane 1, or position 1, which is here. And the second plot, we told MATLAB to put that in position 2, or pane 2, which is right here. Alright, so any questions on subplots?
Yeah, sorry, Patrick. What does subplots do again in generally? What do you call it? I got distracted by rain. It was like,
Yeah. So subplots, they allow us to have multiple plots on one figure. So here we have one figure, and within this figure we have these 2 plots.
okay.
Yeah, so that's when you would use it. It's really useful if, I didn't do it in this case, but if we're looking at some function, and we want to look at that function for the entire range of that function, and maybe we want to look at a very specific portion of that function as well. So then we would use subplot.
So what do you call it? So basically, it's to show like a graph. What does it do?
Yeah, to have multiple figures though, or multiple plots on that one figure, it allows for a really easy comparison.
Oh, so it's a comparison thing.
I mean, that's what it's typically used for, but it depends on your kind of application.
Oh, okay, got it.
Okay. Alright, so there's a question, would subplot 1, 1, 1 look at the top left? So if you did subplot 1, 1, 1, that means it's only one row and one column and one pane. So it's basically like a scalar. So it wouldn't be the top left because you only have one option. So I wouldn't say top left because, again, in this case, all you specified was one row, one column, and one pane. So that would be like we only basically made just a regular plot. But if you have like a subplot, maybe let's say 2, 1, 1, that would be like if we had 2 rows and then I was in the first column and the first pane. So let's make a matrix. Why not? Because that would, or actually we could just do a whole new subplot. So I'll do subplot. We'll do 2, I should do 2, 2 actually, and then comma 1. Subplot 2, 2, 2, 2. Subplot 2, 2, 3. I'll fix that error. I see it. 2, 2, 4. Let me turn this off. So, in this case, I did subplot 2, 2. That's the more important thing to first think about. So that means I want to make a subplot that has 2 rows and 2 columns. So it's, kind of like a matrix, right? Or it's an array of plots. So if I want to look at the top left, that would be 2, 2, 1. That means, for all of these plots here, we have to put 2, 2 because they belong to this subplot that has 2 rows and 2 columns. But if I want to look at this top left one, that would be this one right here. That's our first pane or our first position. So that's this one. And the second one, the top right, that would be this one here. So comma 2. And the bottom left, it would be comma 3. And then the bottom right would be comma 4. So top left, top right, bottom left, and then bottom right. Alright, so does that make sense?
Why did you have to put percentage?
I just made a comment for us, just so we know that, oh yeah, this is the top left one, this is the top right, and so on. So we don't need that percentage.
So percentage is just like a comment overall.
Yeah, you always need a percent if you want to put a comment. Okay, so if there's no more questions on subplots, then we're gonna move on. Okay, so we're gonna move on to data markers and line types. So this is when okay, there's a question. So 1, 1, 1, that would only have 1, and yeah, that's correct. Basically, if you did subplot 1, 1, 1, you're really just using like a regular old plot command essentially. Yeah, look at it like it's a matrix. Yeah, that's what I'd recommend. Yeah. Okay, so data markers and line types. So this will be basically talking about colors, talking about different line types, so like a solid line or a dashed line or a dotted line. And then data markers, that'll be like when we have a circle or maybe a square or a star for each point that we plot on our graph. So let's make this bigger. So from past plots, you've seen that we could use a data marker, which would look like this. This is a circle data marker. So here, in this plot here, what I did is I made, I don't know what I called it, just a regular plot. So you see in my plot line right here on line 3, all I did was plot x comma a, and I plotted this function here. And that's fine, but it's not telling us too much. Like, so sometimes we actually want to see where our specific data markers are. So you'll see this once you go into like EGME 306B, the fluids lab. There are certain labs that you'll do in there specifically where you're going to collect a lot of different data points in the lab and you're going to plot it later on. And you actually want to show, you want to use a data marker for each data point that you have. Because when you have just a straight line, you're kind of implying that you have more data than you actually have, because it's this straight line kind of interpolating between these two different points. So if you use the data marker also in addition to this solid line, so something like this, then we get a better idea of the data points that we have. But so that's more of a practical kind of example of when we would use both a solid line and use a data marker like these circles here. So let's go over on how we can actually do this though. So first we'll make a boring plot. So we're going to do x equals 0 to 10, and we're going to use a step size of 1. So we're only going to have a length of 11 here. Oh, I just closed out of my slides. Okay. So right now this is a row vector that has 11 elements in it because we're going from 0 to 10 with a step size of 1. Now let's get our function, we'll do y, and we're going to call this 5 times x cubed. I don't need this period like I have in my slides. So we're going to do 5 times x cubed. So I don't need a period here because what we essentially have is a scalar multiplied by a vector. This is our vector, which is x to the third. And since we're raising that to the third power, we do have to use an element by element operation. But from that, we're multiplying that vector by a scalar, so I can just do 5 times x cubed. Let's turn this off. So we can do a nice boring plot here. Plot x comma y. Figure visible on. So here's our boring plot. But like I was talking about before, this is kind of implying that we have more data than we really have. We only have 11 discrete points on here, but this is a smooth line, kind of implying that we have a lot more data points than we actually have. So in something like this, if we have not a ton of data points, it would be more wise and more useful to show data markers as well. So to do that, I'll first show you just having data markers and that's it. So basically like a scatter plot. So I could do x comma y, and if I put in quotes here, in single quotes, in O, that stands for a circle in MATLAB. So if I run our code now, this is the plot that we get. So it's only plotting the data markers that we have. And for this function, we can kind of see the trend. But if we had something like a sine wave or a cosine wave, and we only had a few data markers like this, it would be harder to visualize that. So in that case, we want to have both data markers and a solid line. And to do that, we just add on, if we want a solid line, a dash. Now if we run this, we have our line, our solid line, and our circles. And I think the order does matter here. So, I have an O and then a dash, but let's try a dash and then an O. Okay, that actually does work as well. So sometimes I think the order does matter for this kind of stuff, but in this case, it actually worked if we have a dash first and then an O, or an O and then a dash. just because I always do it like this, I'm going to do that. So if I also want to make this, let's say, red, I just put an R in front, so that stands for red. And there we go. Now we have a plot with that's red and has data markers and also has a solid line. So let's see, can I put this at the end here? Yeah, I can even put that at the end. Maybe that's new too. I swear before the order mattered, but maybe not. Let's see, let's try this. I'm just curious now. That works too. Okay, so that's useful. So here are some of the data markers that we have inside of MATLAB. So we have a dot, which will just be a dot or a period. We can have a star, which is going to be a star. Across is X, circle O, plus plus, square is S, diamond D, and a 5-pointed star is P. Line types, so a solid line like we just did now is just a dash. A dashed line is 2 dashes. A dash dotted line, dash dot. And a dotted line, we put a colon. And then for our colors, we have, these are kind of the main colors that MATLAB uses where we can just specify a letter. So black is K, blue is B, cyan C, green G, magenta M, red R, white W. We're never going to use that unless we actually change the background color, of course. And then yellow, which I would also recommend not using if you have a white background, that's why. And I think there was a question earlier on in the semester if we can specify different kind of hues of colors. So you can do that, but you have to actually specify the specific RGB values. And I forget the exact syntax for that off the top of my head, but you can do that too.
Patrick, what's the dash or do again?
What's the what?
What does dash or do again?
So we can have a dashed line with these 2 dashes. Is that your question?
Oh, it has nothing to do with the or.
No, this is just for the actual curve. So if I go back to our example that we did, if I did like R dash dash, then those 2 dashes, that's just going to affect how the line type is on our curve. So now it's a dashed line.
Okay, I see. So this is pretty much important for the COVID-19 thing again.
Yeah, I mean, yeah, depending on what we're plotting, yeah, it would matter for the line type, yeah.
Okay, I see.
Okay, and then just because we're running out of time, I don't have enough time to do another example. Let's do like RS. That's going to be red squares. And see, I didn't connect anything here, so let's do RS. And let's do a dash dot line. So that's a dash and then a dot. And there we go. We have, it's a little hard to see right now, but we have dashes and then dots. So anyways, that's it for today. I want to show you guys that we didn't get through as much as I wanted to just because of the review in the beginning. So homework is going to be assigned on this upcoming Monday. We should be able to get through the rest of the slides, and then I'll upload the homework then. So yeah, that's it for today though. So you guys are free to go, and I'll see you all on next Monday.
Can I talk to you when everyone's gone, Patrick?
Yeah.
Thank you, Professor.
Have a good day.
Thank you.